Yes. We now proceed to the first session of the GIAN course on green ammonia, a key player in the carbon-free energy revolution. I invite all the attendees to stay with us. We start the course with the lecture 1, Introduction to Green Ammonia Production Technologies by the Professor Jianli. Now, I would like to invite Professor Musa to start the session with this lecture. It's over to you, sir. Sir, it's over to you, sir.
Hello, can you hear me?
Yes, sir. Yes, sir, we can start the session. It's over to you, sir.
Okay, so do we have a student in the classroom already? Should we wait for a couple minutes or we can start now? I'm ready. Hello?
We can start. We can start.
We can start now?
Yes, we can start now, sir.
Can everyone see my slide?
Yes, sir.
Yes, sir, we can see the slide, sir.
Okay, cool. All right, good. Hey, good afternoon, everyone. This is the session 1, day 1, session 1, introduction to green ammonia production technologies. Dr. Anand, and we talk several times, and then we kind of from the beginning, we want to give a introduction on why the green ammonia production. There are many technologies we are going to lecture in the next 2 weeks. So, but let's begin with what's the green ammonia? For the online lecture, it's very difficult to point out the name of a student. So if I want to treat this as interactive, the lecture, okay? Don't just listen to me. I can talk for hours without stopping, but I want a student interrupting me, asking questions, or when I ask questions, I hope the student responded, okay? So that's the way I teach in here in the classroom. But I expect the student in the audience asking questions or answer the questions, so we get into the discussion mode. Okay. So, all right. So, when I talk to Dr. Anand, I understand the audience has the PhD students, first year or second year, major in chemistry, chemical engineering, mechanical engineering, and then maybe material science. How many students do not understand the equation? I want to make sure. Do you understand the nitrogen plus 3 hydrogen give ammonia? Everyone knows chemistry? I just want to make sure. Could you say it again? I could not hear you.
Yeah, basically we know about ammonia and how to synthesize or something like that. We have that before research.
Okay, so you all understand the chemistry. I just want to make sure. Yeah, because when I teach this course, something similar courses in the West Virginia University, there are some students from the different major. They couldn't even write equation. I say, well, if you cannot even understand the chemical equation, you probably should not take these courses, because when I talk about the thermodynamics, equilibrium control, they're all related to chemistry. Luckily, ammonia synthesis reaction is very simple. You have nitrogen, hydrogen, you make ammonia only. You do not make any other byproduct, which is good part of ammonia. So, all right. So, from the, you understand, I hope audience can say something, okay? How do you know about ammonia? Ammonia, I mean, you can read my slide. Ammonia process was invented in 1909 by these two gentlemen whose name is last name Haber, Fritz Haber and Karl Bosch. I think one of them got Nobel Prize or maybe both later on. I think 1913. So the process has been commercialized 4 years later by a company called BASF. I'm sure BASF is a German company, has a branch or the subsidiary in India, because I think I have student, Indian student went back to work in India. I think she worked at the BASF. So typically Haber Bosch operate at 420 to 520 degrees C, and the pressure range from 200 to 300 bars. Look at the first reactor in the picture. The reactor wall is very, very thick. You are talking about 8-inch. I'm sorry, I do not convert the inch to the centimeter. I think 1 inch is 2.54 centimeter. This reactor wall is 8-inch, so 8 times 2.54. That's high pressure reactor. And then if you look at this reactor, in the old days, they cannot machine the reactor very long. You see that in the middle, they still have a flange. Today, you don't machine that way. You basically weld it. You don't want to use a flange. Okay, I'm going to stop here and asking questions. Let's get into discussion mode. What do you know about ammonia? Why ammonia? Can anybody answer my question? What is ammonia?
It's not very
Hello. Yes, sir. Ammonia is used by the plants for their making of proteins and all other compounds. So basically, plant cannot take the nitrogen directly from the atmosphere. So they take up the ammonium nitrate, ammonia in the form of ammonium nitrate, and they take in their body, and they helps. It is through different cycles. It is converted to a plant proteins.
Thank you. I'm so happy the student answered this question. Okay, so basically in the old days, before the Haber Bosch invented this process, the ammonia is from so-called biological fixation, all right? So basically the root of the plant basically take nitrogen and turn that into the fertilizer. So very good. So now my next question is, if the plant or the crops or the trees or the grass can do ammonia or can turn nitrogen N2 in the air into the fertilizer or ammonia, why do we do the ammonia synthesis for almost more than 111 years? Why ammonia synthesis is so important?
Sir,
Yeah, go ahead.
sensation is done using the roots of the leguminous and rhizobia plants, sir, which are in a small scale. So the nitrogen cycle during lightning, the ammonia fixation is highest.
Yeah.
So it
Very
is
good.
natural cycle. It is occurring every time. So we can't synthesis from nature directly ammonia.
Yes. Okay. Perfect. I really like this student's answer. Did everybody hear what he said? The lightning, basically lightning turned the N2 nitrogen into the something equivalent to the ammonia or equivalent to the nitrate or NOx that become fertilizer. The key word is lightning. So in one of the lecture, we are going to talk about the plasma. That's basically mimic the lightning. Okay. So let me back to the topic. So why the world is so much the interest in ammonia? I'm not sure if any students in the audience come from the farms, or you parents or you the grandparents are the farmers. My grandparents are farmers. I basically work in the farm. what's the fertilizer composition? If you try to grow the, let's say, the corn or rice, you need to apply the fertilizer. What are the elements of fertilizer? Anybody can tell me? What's the three components? I give a hint. I give a hint. Yeah, go ahead.
NPK, nitrogen, potassium, and phosphorus.
Thank you. Yes. So nitrogen, potassium, and phosphorus. All right. And then if you go to the supermarket or any I would say the greenhouse, try to buy the fertilizer for anything like grow in your backyard. If you read the label, more than 70% are the nitrogen. Okay. So and then potassium and the phosphorus is remaining 30%. So you need a lot of nitrogen. Before Haber-Bosch, in the old days, if you watch the movie, how the farmers acquire the nitrogen. Anybody can tell me before the ammonia or the urea fertilizer, before these two gentlemen, the picture here, how the farmers acquired nitrogen?
Hello? You have a question?
Go ahead. Where are the nitrogen? In the old days, let's say the 200 years ago,
Through green
in the
manure.
world, where were the farmers acquire the fertilizer? There's no ammonia. Go ahead.
Through green manures, green leaf manures. Cow dung,
Okay.
cow dung, like that.
Yes. So basically, you take whatever you can from the I would say any the material from the field, and then actually the most famous, the popular nitrogen fertilizer is the manure. All right. So basically, in the old days, it's called chicken poops or the cow manure. They basically take it, apply in the field, but the production yield is very low. Let's say 1 acre probably produce like very little the crops because you don't have enough fertilizer, because that's the old days of agriculture. If you look at today, because you apply the urea or the ammonia or the fertilizer, I think the the productivity of 1 acre of land grow much faster, much more. All right. So to say different way, without these two gentlemen, there will be World War IV. You heard about the World War III, World War II, all right? There will be World War III, IV, V, VI occurred until now. The reason being that people competing the land for the food. Because these two gentlemen, we don't care about the food because the per acre we can grow a lot of food. I don't think today you can talk about the shortage of food. I'm not sure about India, China. But in US, actually we turn food into the fuel. Let's say the corn, 70% corn made into the gasoline and the diesel. So what does it mean? That means because of per acre, there's so much ammonia or the fertilizer applied, they grow fast. So back to the topic. The reason we do not rely on the biological process of the plant to fix the nitrogen because it's too slow. Biological process too slow. Haber-Bosch process so fast. You can provide so much the quicker ammonia production, and then the basic apply to the field. So I don't know if anyone knows. Can anyone tell me ammonia? What's the ammonia? I mean, if you rank the chemical in the world, any chemicals, sulfuric acid, polymers, and whatever you understand, what's the position, what's the ranking of ammonia in terms of production? Number 1, number 2, number 3, anybody can tell me? You can do the internet search now, but anybody from top of your head, anybody knows ammonia?
No, ammonium chloride, it's explosive release also.
Could you repeat your answer again?
Ammonium chloride.
Yeah. Okay. So ammonia is the second largest chemical in the world. Nobody knows. All right. So basically, people take ammonia for granted because you don't know. Ammonia production per year in the world is 195 million tons per year. 195 million tons per year. If you look at any chemicals, that is not even near ammonia. There's so much of the production of ammonia in the world, but because it's the industrial process is over 100 years, people take it for granted. But we have to appreciate these two guys. Anyway, so what is important about ammonia? Number one is the agriculture use. Because ammonia per acre production is so much, we do not compete the land. That means you don't see one country during the World War I, World War II, invade another country and then occupy the land because that's agriculture economy, all right? Today's economy is not agriculture. If you own the land, nobody cares because the land per acre can produce much, much more food than you need. As I said, in US export the corn and also the soybean, any agricultural product because there's so many, the production is so high. So that let me repeat one more thing. Because of ammonia, compared to 100 years ago, per acre productivity increased 40 times, 40 times, which means if you back to the clock, the day to the 19th century, each acre, if you produce each acre like X, today times 40. It's just amazing, the ammonia fertilizer. True, you pay the price because the ammonia is very expensive. Okay, so anybody have any questions? So this is the background why ammonia is important, and this is the chemistry. And also keep in mind, ammonia is a very high pressure, high temperature. I'm gonna talk about why ammonia need a high temperature and high pressure. Anybody have any question before I move to next? Okay, I'm going to move to the next slide. All right. So if you look at this equation, ammonia production, you have nitrogen, hydrogen, and make ammonia. All right. We all know nitrogen can be separated from air. All right. That's a commercial process. It's called cryogenic separation, and you have nitrogen. The key is hydrogen. The majority of the cost of is hydrogen. So talking about the green ammonia, we have to talk about the green hydrogen. Make sense? So green ammonia okay, it's not required. Green ammonia requires, I'm sorry. There's a typo here, requires green hydrogen. So I already mentioned about what's application of ammonia. It's the major things is agriculture, all right? Anybody can tell me the other use of ammonia? How do you look at the first picture? If that give you a hint, I want you to tell me how what's the other use of ammonia?
For refrigeration application, we can use ammonia.
Okay, good. Yeah. So everyone has do you have a refrigerator at home? Everyone has a refrigerator?
Ammonia is used for fertilizer, and nowadays we move on to ammonia as fuel.
Yeah.
I think.
So if you look at, yeah, let me get my pointer. If you look at the ammonia application, I think more than 50% ammonia today, among 190 million tons, are used in agriculture. And then some other use the ammonia like as a transportation fuel. But in the old days, ammonia actually they use as dynamite, explosive. So you can turn ammonia into nitrate, all right, oxidized, and then you can make an explosive. So that actually during World War I, World War II, you heard about the company called DuPont, which is not far from here. So they make a lot of the dynamite, the explosive. So then basically that's from ammonia. So that's why the ammonia are highly demanded. So today production still the increase, but pretty much stabilized at somewhere around 190 million tons already. Okay, so talking about ammonia synthesis, I'm going to show you the process flow diagram. So for the student, if you have any questions, just raise your hand, ask question. Otherwise, I will keep on talking. Okay. So true, I do want to ask you the question. So the ammonia synthesis. So there's low pressure and then the high pressure the synthesis of ammonia. Okay, it just depends on how you want to do it. So keep in mind the whole idea of making ammonia, you make hydrogen. I'm going to show you after I show you slides. I want to show you the flow diagram and then how ammonia is made in the industry today. Once you have hydrogen, ammonia is given. So basically, the so-called Haber-Bosch process. Two gentlemen invented in 100 years ago. So, okay, I'm going to go back to my equation. Hold on. Looking at this equation, ammonia synthesis. Can everyone tell me why ammonia need high temperature and high pressure? I'm talking about from you just answer my question from a thermodynamic and kinetic point of view, because it's high temperature, high pressure. Why?
Nitrogen fixation is very difficult. Breaking the bond between nitrogen.
Thank you. Very good. So basically, I hope every student hear what he said. So nitrogen is very stable. It's a triple bond. All right. To activate nitrogen, you need a temperature. So basically, you are talking about the kinetics. Kinetics means you have to make sure you activate the nitrogen. However, if you look at this reaction, this is exothermic reaction. You understand? I hope audience you understand you have chemistry or chemical engineering background. The reaction, the forward reaction called nitrogen plus hydrogen, give out heat. It's called exothermic. Here's a question. For exothermic reaction, is it favored if you increase temperature or unfavored if you increase temperature? It's isothermic. I tell you the answer. It is isothermic reaction going forward. So for isothermic reaction, will temperature help isothermic reaction from thermodynamic point of view? Any chemistry or chemical engineering student can answer my question? I want to get answer yes or no. Again, this reaction is exothermic. That means they release heat. If you increase the temperature, would that help the reaction? Understand my question?
Sir, could you repeat the question?
Okay. So nitrogen and hydrogen reaction to make ammonia is exothermic reaction. You follow me? Exothermic means this reaction give out a lot of heat. Thermodynamically, if you increase temperature, do you help exothermic reaction or you hurt exothermic reaction?
So the question is, so what do you know about the exotherm? How it is coming out?
During the chemical reaction, heat energy is coming out from the process, then we can call that as a exothermic. Endothermic means we have to give heat for completing the reaction. Heat as input, then endothermic. Heat as released from the reaction, then we can call that reaction as a exothermic reaction.
Yeah. Okay. So the reaction is exothermic, and thermodynamically, the increased temperature will not favor exothermic. The reaction already give out heat. If you increase temperature, the reaction will move back, reverse. Make sense? Anybody? I hope that you guys learn the thermodynamics. The thermodynamics means this basically this equilibrium the reaction, all right? So if you increase the temperature, and then the reaction will go equilibrium will go backward. So So basically, the one student says you need to increase the temperature, high temperature, because you need active nitrogen. That's called kinetics. However, when you increase the temperature, the reaction actually not going forward, it's going backward from thermodynamic point of view. Now, I'm asking you a question. By reading this read the equation, if you increase the pressure, the reaction or equilibrium will go to the right or go to left. This high school chemistry. Look at this equation. 1 nitrogen plus 3 hydrogen produce 2 ammonia. If you increase the pressure, will the reaction go to right or reaction go to left?
Equilibrium. Equilibrium means you have to give arrow both sides. Nitrogen can
Increase the pressure or the force right direction.
Thank you. Who says that? I think someone I heard says increase the pressure, reaction go to right. Is that right? Yeah. It's Richard law. Is that right? It's you should. I'm pretty sure you learned this from high school. You have 4 molecules on the left hand side. You have 2 molecules on the right hand side. You increase pressure, go to right. Okay. All right. So this is the reason. Okay. Now come back to the point. Okay. So I'm glad we come back to this one. It looks like some student you probably need to fresh your memory on high school chemistry. If you have in gas physics reaction, if you have more molecule on the left hand side, less molecule on the right hand side, increased pressure will force equilibrium to the right. All right. So for exothermic reaction, the increased temperature will force the reaction go to the left. So they are against each other. So look at this. So I think the student just mentioned that you need high temperature to active nitrogen. He's correct. That's why these 2 gentlemen 100 years ago he tried high temperature, but he got a very low yield. The reason being that at a lower pressure, the reaction will not go to right. So they had to increase the pressure to force the reaction to go to right. So they counter each other. That means, number one, for kinetic reason, you need a high temperature. You follow me? Because you need active nitrogen. For the thermodynamic reason, thermodynamic means that you have to force the reaction to the right, you have to increase pressure. So these 2 gentlemen, the reason they got Nobel Prize, this is one of the reasons. These 2 gentlemen, they tried 4,000 catalyst formula. Read the history. 4,000 catalysts means probably more than 10,000 experiments. I think they deserve Nobel Prize. Then they fixed the temperature in this range and pressure. Look at that reactor. That's the first reactor this guy ever made, 1913. So I hope you guys understand the why Haber-Bosch is so challenged, because you need a high temperature and high pressure. Okay. Yeah, just asking questions the next time. I think I don't want to keep on talking. You don't understand what's meaning here. Okay. So the first cartoon shows the application of the ammonia, agriculture and industry use, and even for the plastic or some kind of let's say the nylon. I think in your clothing, if you use nylon, you also have a nitrogen from ammonia, and also the dynamite. Ammonia synthesis by Haber-Bosch process, the most expensive of ammonia synthesis is hydrogen. So in hydrogen coming from coal, I'm pretty sure in the country like India, China, because you don't have too much natural gas, your ammonia is coming from the gasification from coal. Same with China. I visit so many ammonia plants. It all come from the solid fuel. In United States, more than 90% of ammonia coming from natural gas, steam reforming. So it's so easy, it's so clean, because you have natural gas, you turn natural gas into hydrogen, and the hydrogen go to ammonia. But in other countries, if you don't have natural gas, use it from coal. So if you look at this, the flow diagram, turning coal into the coal gasification and reforming into hydrogen, it takes a lot of effort. I'm not going to talk about coal gasification in the next 2 weeks. I'm talking about the renewable power. What if you have a renewable energy? You can use the renewable, the solar and the wind, but you can do electrolysis. Once you electrolysis, you turn water into hydrogen. Okay, so that's a process we are making, and also there are some other unconventional way to make the ammonia. So ammonia today can be the liquid fuel. You can burn ammonia. I think today some of the Japanese the coal-fired plant, when they generate electricity using coal, they back out 30% coal, replace the ammonia. You can burn ammonia together with the coal, so basically lower the emission. And also, of course, you can turn ammonia and then into fuel cell. There are some ammonia fuel cells, so you don't have to turn ammonia back into hydrogen. You can turn ammonia into use ammonia directly as the fuel cell. There are some ammonia fuel cells. Yeah. Anybody have any questions so far? And ammonia is a liquid. Okay, so you look at this yellow tank, and then actually inside the tank is in a liquid form, ammonia. So you can. That's why ammonia can. I think one of the speakers today mentioned about ammonia is a hydrogen carrier, and then it's the energy carrier because it can be transported as a liquid using pipeline, using truck, and by all means transported. Okay. So again, green ammonia is all you are all talking about green hydrogen. So this picture really shows U.S. Department of Energy spent a lot of the money, effort. Is the program called Hydrogen at Scale. Actually, I got the funding, research funding from this process, and also the hydrogen is color coded. Okay, when I say color coded, and have everyone heard of a blue hydrogen?
Hydrogen is produced from carbon resource, but that carbon is completely captured by carbon capture.
Thank you. You are right on mark. Thank you. So basically, today we are talking about green ammonia. So that means the hydrogen has to be green hydrogen. Where are the green hydrogen? So green hydrogen has to come from the renewable power, biomass, and then the defined as green hydrogen. But there are some other hydrogen. They are not necessarily green, but they are clean. So for example, blue hydrogen, you can turn methane into the hydrogen, but you have to sequester CO2. It's not green, but it's clean. So that's why today in the United States, we are talking about clean hydrogen, not necessarily green hydrogen, because the production of green hydrogen, the quantity produced per year is so low. So this cartoon really shows different way to make the green hydrogen. I mean, make a clean hydrogen. That's why they call it Hydrogen at a Scale program. So I'm heavily involved in from the natural gas to make the hydrogen. Okay, so you can use the nuclear. Nuclear is a different story. I'm not going to talk about nuclear. So somebody say hydrogen from nuclear is called pink hydrogen. It's a subject to a lot of debate. But the nuclear that doesn't, if you use the nuclear power to do electrolysis, the hydrogen doesn't generate CO2, but it's not green. It's called pink because the nuclear is subject to the different environmental issue. Anyway, so you can do the Google and find out the slide. It's a very I would say very large program and developed by the U.S. Department of Energy. And also today, this program expanded into the hydrogen hub. So U.S. federal government invested $9 billion and then the develop 6 hydrogen hub, $9 billion a lot. So the 6 hydrogen hub. So we are located in West Virginia. We are in the hydrogen hub, turning shale gas into the hydrogen. And that's true. Ammonia is a part of this the hydrogen hub because is transportation. Okay, so if you I don't want to go through the detail how you produce ammonia. There's a different way to produce ammonia, and you know that you can use the so-called the different power, renewable, that's green, and then nuclear, and also fossil. And yeah, there are different ways to make the hydrogen, and then which will turn into ammonia. Okay. All right. So this one is very talking about. Let me ask the question for the audience. I hope the audience you have a little bit of knowledge about the so-called process flow diagram. Throughout my lectures in the next 2 weeks, I'm going to use this. I would say the high level the flow diagram to illustrate the concept. Okay. I hope you understand this, but I can send you some literature and for pre-read. Otherwise, if you don't understand the process flow diagram, it's very difficult to understand it. Okay, so I will try to slowly interpret this. Ammonia synthesis. We all talk about the hydrogen. All right. If you walk in the Haber-Bosch plant, look at my circle, my pointer. So more than half of the unit in the Haber-Bosch plant are like this. You see my circle? Basically, you are producing hydrogen. So how do you produce hydrogen? You need to have the fuel come in, and then let's say the methane. By the way, in the United States, they are all talking about the methane steam reforming, and you have methane steam reforming to make hydrogen, and then you do the air separation. You see the methane coming in. You see the methane coming, go to top. The top half are the hydrogen production. You go to the top and go through the steam reforming, water gas shift, and at the end, you produce hydrogen. And then the hydrogen compression and feed in the Haber-Bosch reactor. See this hydrogen coming out? And then basically the multi-state feed compressor will feed Haber-Bosch reactor. And look at how complex this is the unit operation. Majority of the unit, and by the way, when I say unit of operation means each vessel is one unit. Okay, there's so many unit operation, whereas the Haber-Bosch is only the one of part of the reactor. A lot of people say, "Oh, I'm going to visit the Haber-Bosch plant." If you go to Haber-Bosch plant, you probably only see Haber-Bosch in the corner. Majority of units are this. So basically, you have the hydrogen produced from the methane steam reforming, and then the feed into the Haber-Bosch reactor. After reactor, ammonia production is not 100% conversion. Let me go back to this. Let me go back to my first slide. So this reaction is not going to complete. It's the equilibrium control. What does it mean? Nitrogen, hydrogen will not reach 100% conversion. That means they are going back and forth. All right. So at a given time, you will see in your reactor you have ammonia, nitrogen, hydrogen present together because they will never go to complete. Follow me? So that's the nature of the ammonia synthesis. So what's the challenge of ammonia synthesis? Passing through the Haber-Bosch reactor, look at these three guys. You have ammonia, hydrogen, nitrogen. You need to separate it, all right? So you have to separate, harvest, recover ammonia, then the hydrogen, nitrogen recycled. Because you don't want to waste hydrogen and nitrogen. They are very expensive because it takes the effort to make nitrogen, takes the effort to make hydrogen. So after you separate the ammonia, these things has to be recompressed, see the hydrogen, nitrogen recycled. They call recycle. So let me repeat. Ammonia reactor, single pass conversion is not 100%. Single pass conversion means this, see the yellow arrow, yellow arrow. The passing through ammonia, that's called single pass, one pass. It's not 100% because you have ammonia, nitrogen, hydrogen. Then you have to do condenser, separate the ammonia, and recycle back. So you have to do recycle, have a second pass. So essentially, hydrogen, nitrogen has to go through the ammonia reactor several cycles before they are fully converted. Make sense? Anybody has any question, just raise your hand. If you don't understand on the left-hand side of the Haber-Bosch plan. So this is, yeah, go ahead. Yeah, please, because of the audio, I cannot hear clearly. Please speak very slowly. Okay, just like what I'm saying. Yeah, very slowly. Go ahead, ask a question.
Actually, by the process, we are producing ammonia as well as unreactive gases. Nitrogen and hydrogen also present in that mixer. So how we can segregate these things? Actually, we are feedbacking the hydrogen and nitrogen alone back to the reactor. Ammonia alone is segregating.
Yeah.
So actually, that segregation part is not easy. So in what way we can segregate, sir? Easy.
Okay, so basically, I think that's a very good question. You are saying that hydrogen and nitrogen, they are not condensable, and then the separate for ammonia is a challenge. And then, is that right? How do we separate? Is that your question?
Yes.
Okay. Did you see this blue condenser? I think that's a very good question. You see the blue condenser? It's called a high pressure cryogenic condenser. What does it mean? You have to compress this gas, hydrogen, nitrogen, and ammonia, then they chill it to, I forgot, I think it's minus 30 degrees C something. You have to chill the whole thing. It's called chilled ammonia. However, under high pressure and the under the low temperature chilled cryogenic condension, hydrogen and the nitrogen will not condense. You see the condenser? They will not condense, so they are going to be recycled. It's a yellow line. That hydrogen, nitrogen will always stay in the gas phase, whereas ammonia will be condensed out. You follow me? So you see this is the compressor. You have to compress ammonia, and then chill this condenser so that ammonia can stay in the liquid phase, and then the hydrogen and nitrogen will be recycled.
Yes, sir. By condensing the ammonia, we can segregate ammonia alone, and we can resend nitrogen and hydrogen. That is fine, sir. But actually, the energy required for condensation is very high.
Yes. Yes. Very good question. Okay. So basically, very good. Very nice. That's how they design the. That's how they design this is the Haber-Bosch plan. In I think in day 3 or day 4, we have a separate lecture, the topic. I think Dr. Anand did a very good job putting together a so-called economic of the ammonia synthesis. In there, we are going to talk about energy balance and the economics. Where the cost, energy cost of a Haber-Bosch plant. You follow me? And also economic, how you save the energy. Because you're right. See this refrigeration compressor and also the cryogenic, the condensing, that costs a lot of electricity, and then a lot of the power. So you're right. It's not efficient, but that's how they design today. Haber-Bosch plant has been there for 100 years. Today we are doing unconventional unconventional ammonia synthesis. We do not call this our process like a microwave, plasma. We do not call them Haber-Bosch process anymore because the pressure temperature are low. It's unconventional, so we do not have to use condenser. Okay, we can use the solvent, ammonia solvent, and we can use the membrane. Okay, separation. Very good question. I think today is day 1 and also lecture 1. I really enjoy the talking to student. Please interrupt me like this student asking questions. So this condenser. I think if you look at the Haber-Bosch reactor, remember I said Haber-Bosch process, the ammonia synthesis is isothermic. Essentially, you do not inject any energy in the Haber-Bosch reactor. Haber-Bosch doesn't need energy. The moment it started, you actually have to take out the heat, remove the heat. So it's really self-sustained Haber-Bosch reactor. it is this back end consume a lot of energy, give or take, for every kg of the ammonia produced, you need 7.8 million BTU, the equivalent of the energy injected. The energy doesn't go into Haber-Bosch reactor, actually goes into this compressor and then the condenser. Make sense? So very good question. When I hope some of you have the senior design in your. I know you are all the PhD students. Okay, so in your senior design, chemical engineering, you probably have any chemical plant design. If you work in any chemical plant, refinery, okay, in any unit operation, let's say this unit, okay, any unit operation, if you watch the unit operation, you have two set of pump. It's called a pump A and pump B. Okay, so any small unit, pump A is running, pump B is standby. Why you need extra pump in there? Because when pump A goes down, you pump B going in. You follow me? I'm talking about the pressure pump, and that's for the small unit. So over some even design the ABC, all right? So if you go through the senior design courses, you will see those design. They always, the instructor always asking put in the extra pump in there. There's a reason for that, because refinery or chemical plant is operated 24 hours, 7 days. You cannot afford one pump going down, you shut down the whole plant. So that's why you always have backup, any unit. Understand? Now, for this condenser, look at my circle. It's a blue condenser. This is refrigeration compressor, recycle compressor. These are three things. They are so big, so expensive, you cannot afford to have a backup. So that means if there's three units, three compressor going down, the whole plant shut down. However, look at this compressor in here. I'm pretty sure they have backup, but for these three on the Haber-Bosch backend, there's no backup. So that's the problem. That basically tell you how complex, how much the money you need to spend in order to get a backup. So they are very critical. You want to operate in such a way they are very stable. You cannot afford shutdown. One day, every ammonia plant you are shut down, you are talking about a couple $1 million. So that's a lot of money if you shut down one day, and then it takes you 5 days to start. So, all right. So if you don't have any questions, Haber-Bosch plant. On the right-hand side is today people try to renovate Haber-Bosch plant. When people renovate the Haber-Bosch plant, they say, I want to produce green ammonia, but I want to utilize existing infrastructure of ammonia, but I just take out all those the hydrogen from fossil. You see this? So that's why they do the electrolysis. And then basically you do electrolyte water, electrolyte again. Electrolysis, the electricity has to be renewable power, all right? Then you do the electrolysis, and then the hydrogen feed into the Haber-Bosch plant. So this is people try to follow, and then to build green ammonia plant. Today, there's no ammonia plant at industrial scale. There's no, well, let me back up. Today, there's no green ammonia plant like on the right-hand side in the United States. I'm asking question. Why? It looks pretty simple, all right? So electrolysis, PSA, pressure. PSA means the pressure swing absorption. You can do the separation and then have nitrogen, hydrogen from electrolysis, feed it. It's so simple electrolysis, and much simpler than this steam reforming natural gas. Why it's not today in the United States? Why it's not in India? I doubt even India has this. I'm talking about reasonable industrial scale, like maybe the 200 or 500 tons per day. Anybody can tell me why? What's the cost of the Haber-Bosch plant on the left-hand side? I already mentioned that. Green ammonia is all about green hydrogen, all right? Anybody can tell me why such a simple process is not commercialized? You are thinking about from economic point of view. Go ahead.
Large scale electrolysis to produce hydrogen is not that much easy as you mentioned early. This look like a simple schematic, but actually it is not that much easy for bulk scale. Still, we are purely depends on carbon-based ammonia synthesis only. Because compared to electrolysis, carbon-based synthesis is easy.
Thank you. Thank you. So when you say not easy, I think you're talking about technical challenge, all right, for electrolysis. And also do you mean by the economics as well?
Yes. Actually, electrolysis process also have lots of technical challenges to run continuously.
Yeah.
Compared to this, carbon-based ammonia synthesis processes has less challenges as of my knowledge and.
Thank you. Very good. I really like this student. Okay, you answer my question. All right. So why this is on the right hand side electrical driven is not commercialized? Okay, let's say that the technical issue. Okay, so Haber-Bosch plant, give or take, the smallest one I ever work on is 1,000 tons per day. I'm going to repeat, 1,000 tons per day ammonia. That's huge. So some Haber-Bosch plant build 200 tons per day, and 2,000 tons per day. So what does it mean? That means it's all about economy of scale. If you learn chemical engineering, even maybe the mechanical engineering, if you build the chemical plant or the petroleum refinery, why people try to build a larger? Because of economy scale. The larger, the better, all right? The larger means the per unit production is smaller. Okay. So now to scale up the electrolyzer to match with today's Haber-Bosch is a challenge. I think that student said a very good, point out very good. What's another challenge? Have you ever heard of, I forgot, is that you dean or the department chair speaker this morning gave us a speech. Have you heard of the renewable power intermittent nature? You understand what I'm saying? Intermittent nature. Anybody can tell me what's the intermittent nature of the renewable power? What about solar? Solar, can you produce electricity 24 hours, 7 days? And the wind? Anybody want to answer this question?
Because during night time, sir, it's seasonal. So this intermittent function changes the areas.
Yeah. I think this morning, one of the professors mentioned about intermittent nature of renewable power. I don't know if any of the students catch what he said. It's very important for the green ammonia or green hydrogen, because when you use green power, it's a fluctuate. It's not 24 hours 7. So none of the electrolyzer today can handle the startup shutdown, which means start from 9 o'clock in the morning and then run into 4 o'clock, and then you have to shut it down. Electrolyzer cannot do that. Then next day in the morning you have started. So typically Haber-Bosch plant is designed to operate 365 days per year. True. Sometime after a couple of years you have to shut it down to maintenance, but that's not the case. The case is electrolyzer is very expensive. Today I can give you a price. Hydrogen from the steam reforming and supplying the Haber-Bosch plant is $1.50 per kilogram by weight. 1 kilogram hydrogen from steam reformer is $1.50 today. So there's a transfer price between the steam reforming and the Haber-Bosch plant because they operate on the same side. It's even lower than $1.50 per kilogram. Today, the electrolyzer, the hydrogen from that it's more than $5 per kilowatt hour. U.S. Department of Energy is shooting for $2 per kg. Try to compete with the natural gas. Hydrogen from natural gas is still cheap. True, you need to put a CO2 on the side. Just compare the hydrogen cost. So because of the cost, if hydrogen costs 3 times more than Haber-Bosch hydrogen, of course nobody will buy the green ammonia. All right. So that's a challenge. The third challenge, I hope someone in material science and or in the mechanical engineering understand fuel cell. In one of the lecture, I'm going to talk about solid oxide fuel cell or the solid oxide electrolyzer. Okay, so the basically how we produce the hydrogen using the solid oxide fuel cell. Basically, you run reverse. So another problem, electrolyzer. Everybody knows the electrochemical there, right? You have an anode, you have cathode. The cathode material has to be iridium. Iridium in the periodic table is IR, iridium. Okay, so for whatever reason, nobody can replace it. Has to be an element. You can reduce the concentration, the use, but that electrode has to contain iridium. So that causes another problem. If all this the green power or the renewable power turn into and supply the electrolyzer around the world, you are going to deplete the iridium in the world. So there are not enough. That's another challenge. Some genius need to find out the different elements that can be utilized for the cathode. I think there's a called ORR, some kind of reaction. Anyway, I hope some of the PhD students in the audience whose research is electrochemical or you can ask the question. I have a little research in that area, but I'm not expert. So anyway, the economic challenge, scale up challenge. Scale up challenge means you have to scale up engineering from engineering side, electrolyzer to match with Haber-Bosch. That cannot be done today. And then the material science problem means you have to replace the most expensive or most precious the metals on the cathode side, and then in order to basically do the massive production of electrolyzer. So anyway, so it looks pretty good on the research side, but when you do commercial, there's a lot of challenge. Anybody? Yeah, you can read. I have this article here. Since we recorded, you can read this the economic analysis. This is a very good article. That's why I basically selected this diagram from this article. So anybody have any questions before I move to the next slide? Just raise your hand and so you can get the microphone and asking questions. Yeah. Anybody have any questions so far? Go ahead.
Professor, can we break for the lunch and can we join up for the lecture too?
Okay. So it's lunchtime now?
Yes, sir.
Okay. All right. So I'm going to the break here. I have some slides. Yeah, we'll continue. How long is the lunch break? 1 hour or is it 1 hour?
Yes, 1 hour, sir.
1 hour. Okay. So we are going to come back in 1 hour from now. All right. Okay.
Yes, sir. Sure.
Thank you. Yeah. See you in 1 hour.
Thank you, sir.
For lunch, come back to be around 2:20.